So Emanuel Milman will talk about functional inequalities on sub-Riemannian manifold via QCD.
Yes, great. Thank you very much, Luca, for the invitation. So, as I said already several times, I'm very happy to speak here. So just a disclaimer before I start, by no means am I any expert in the sub-Riemannian setting. I'm sure everyone in the audience knows much more than me, but somehow I was fortunate enough to stumble across this application to the sub-Riemannian setting, so I'll tell you about this. And it pertains to a functional inequality. So let me start the talk by telling you what I mean by functional inequalities, and I might as well define them on a general metric measure space, XDM. So what is this? XD is just a complete separable metric space. And M is a locally finite Borel measure on this metric space. Okay, so we have this triplet. Given some locally Lipschitz test function f on our space, we're going to use this notation to define the local Lipschitz constant of the function, given by the usual expression. You know, we take the lim sup as y goes to x of the usual quotient of differences. Notice that this notation, I mean, it looks like I'm taking some type of gradient, but of course there's no differentiable structure. This is just a very convenient notation that I speak about the length, the absolute value, the length of the gradient. And of course, the notation is very suggestive because in the smooth setting, whenever, let's say we're on a Riemannian manifold, now this expression is exactly the length, the Riemannian length of the gradient, okay? But this is just a convenient notation. There's no differentiable structure. Okay, so given a subset omega of our metric space, we denote by lambda star of omega, where star will correspond to the particular functional inequality that we're interested in. So lambda star of omega is going to denote the best constant and these inequalities, which should hold for any locally Lipschitz test function f on our set omega. So the first example is perhaps the most, the most common, the most classical functional inequality. This is the Poincarè inequality. So this is the requirement that for any test function f which integrates to 0 on the domain, on the set omega, we have this relation between the L2 norm of f and the L2 norm of the gradient of f. This is called the usually energy. Okay, and the best constant here is denoted by lambda 2. And of course, as we all know, in the smooth setting, if you're in some smooth setting, then you can integrate the right-hand side by parts, and you'll see that this lambda 2 is exactly the first non-zero eigenvalue of the Neumann Laplacian defined on omega. Okay, the first non-zero because f here is assumed to be perpendicular to the constant functions. So this is the meaning of the Poincaré inequality. Of course, you can talk about the LP Poincaré inequality for p between 1 and infinity, which is the requirement that under this now natural balancing condition on f, you want to have this relation between the LP norm of f and the LP norm of the gradient of f. And the best constant here is denoted by lambda sub p of omega. And finally, we'll say that a log-Sobolev inequality holds if for any Lipschitz function satisfying this natural balancing condition, we have now this relation again between the L2 energy on the right-hand side, but on the left-hand side, we take a kind of an L2 log L norm, slightly stronger than L2. You have this expression, well, this division by 2 is just traditional normalization, and the best constant is denoted by lambda sub ls for log-Sobolev. Okay, so what is our goal? We would like to get some non-trivial lower bound on lambda, on our constants, lambda star. By non-trivial, I mean anything positive to start with. And of course, we would like a bound which will depend on the metric measure space we're working on, and let's say an upper bound on the diameter of our set omega. Okay, this would be our goal. However, we immediately see that there is a problem because the way I've set things up so far, there's nothing non-trivial that we can say. The best expression that we can write on the right-hand side here is just 0. And the reason is very simple to see, because for instance, if we choose omega to be a disconnected set, then we can always choose a test function which is piecewise constant on each connected component, okay, and which would mean that the gradient, so we can always choose the constants so that the balancing condition here is satisfied. But on the other hand, since the function is piecewise constant, the right-hand side will just be 0, the left-hand side will not. So the best constant that we can write here for disconnected sets are, of course, 0. So this means that whenever omega is disconnected, you cannot, these constants are 0, you cannot say anything. So, you may think, well, maybe this is a topological obstruction. Maybe I should assume that omega is connected. But no, of course, the same problem will persist if omega has small necks. By choosing the necks to be arbitrarily small, we will have the same problem. Okay. So the typical solution in the literature to this problem is to assume that omega is in some sets convex, because convexity, at least philosophically speaking, morally speaking, convexity is exactly a property which prevents the existence of necks. Right? And in the metric space setting, the natural assumption is to assume that omega is what is called geodesically convex, meaning that between any 2 points, x and y in omega, there exists a distance minimizing geodesic, and in this talk, all geodesics are always distance minimizing. So there exists a geodesic connecting x and y, which lies entirely inside omega. This is the meaning of being geodesically convex. And under this natural assumption of convexity, then, of course, there are many known results. So the classical results are in the Riemannian setting. So assume that we have a nice Riemannian manifold with its canonical Riemannian volume form. Then if omega is a convex domain, here are a couple of classical results. If the Ricci curvature is non-negative and the diameter of our convex domain is upper bounded by d, then the classical Li-Yau Zhong-Yang estimate states that the Poincarè constant, the first non-zero eigenvalue of the Laplacian, is at least pi squared over d squared, okay, over the diameter squared, and that's a best possible estimate. By the way, so I don't see anyone. Can you just confirm that you hear me? Because I don't even see.
Yes.
Yeah,
Everything is fine.
Perfectly.
Okay.
Perfect.
Okay. Great. So another result of this form is, I don't know who to attribute this to, because this is very well known to experts, but this is folklore. The same type of estimate holds for the log-Sobolev inequality under these conditions. So it's known that log-Sobolev is at least constant divided by the diameter squared. And by the way, if you're looking for interesting open problems, I believe that the optimal value of this constant C is not known. Of course, the natural conjecture is that it should be the same as here, it should be pi squared, but if I'm not mistaken, this is still open. It's a one-dimensional optimization problem, but I think it's not known. But anyway, it's of the order of 1 over d squared. If you assume that the Ricci curvature is not only non-negative, but actually strictly positive, so bounded from below by a positive k, then again, classical Lishnirovich estimate states that the Poincarè constant is at least k times n over n minus 1. So now you see the dimension of the manifold appearing. And again, the classical by now Bakri-Emery estimate says that the log-Sobolev constant enjoys exactly the same bound. Okay. And there are some similar best possible results for the P Poincaré constant, which I do not state here. Okay, but in the Riemannian setting, this is all completely well known in classical. What is the problem? The problem is that we're going to soon move to the sub-Riemannian setting, and the problem there is that geodesically convex domains are very scarce. They almost do not exist. So we cannot use this kind of assumption that we were using before in the Riemannian setting. And my favorite example here is due to Monti and Rickley, who showed that on the simplest non-trivial example of a sub-Riemannian manifold, the first Heisenberg group. So I'm sure you all know, and I'll get to it in a few slides, but for now, you don't have to know anything, just that it's a three-dimensional manifold, let's say, with symmetric structure. Then they showed that on H1, there are no geodesically convex geodesic balls. And this is very different from the Riemannian setting, because we know that on a Riemannian manifold, if you take a geodesic ball of a small enough radius, it's always going to be geodesically convex. Okay, but this is not the case for the Heisenberg group. And in fact, they showed that the smallest geodesically convex set, which contains 3 distinct points do not lie on a common geodesic, because of course a geodesic is a kind of a trivial geodesically convex set. But if you're already outside of a geodesic, the smallest set is already the entire space. Okay, so this is in a very strong sense, basically saying that besides geodesics, there are no geodesically convex sets on H1, except for the whole space. Okay, so we cannot make this assumption as before, just work on convex sets. So what do? Well, our solution is going to be to replace the set omega that we have on the right-hand side of our inequalities, on the energy side of our inequalities, by a slightly larger set, which we denote by geo of omega. Okay, what is geo of omega? This is the 2-point geodesic hull of omega. So you just look at all geodesics beginning and terminating in omega and take their union. Okay, this is a 2-point geodesic hull. So what is this creature? Just a few comments. Notice that the geodesic, 2-point geodesic hull of omega, it need not be geodesically convex itself, which is good news, because otherwise on H1 we would get the whole space. That would be too much. And the reason is very simple. Just remember Carathéodory's theorem that states that if you want to get the convex hull in Rn, you have to use the geodesic hull of n+1 points. You have to take convex combination of n+1 points. So even if you're in R2 in the plane, you look at these 3 points here, then the convex hull, of course, is the whole solid triangle, but the 2-point geodesic hull is just the boundary of this triangle. Okay, so you see that certainly the 2-point geodesic hull is not geodesically convex itself, which is good. Another obvious remark is that if omega is already strongly geodesically convex to begin with, then this operation doesn't do anything. So basically, we're back to the previous settings. So in this sense, we're just generalizing what was done before, because if you start with a convex set or strongly convex set, then this operation doesn't do anything. So again, we're not doing something too strange. And finally, last comment is note that just by using the triangle inequality, then on any metric space, the 2-point geodesic hull of a geodesic ball of radius r is always a subset of the geodesic ball of radius 2r. Okay, this is just triangle inequality. So this means that we're not enlarging our set by too much. So this is a pretty reasonable solution. Okay, so let's go back to our functional inequalities. And you see on the right side, we make the set a bit larger. We take the 2-point geodesic hull. And now our question makes perfect sense. Now we can try to find some interesting, some non-trivial lower bound on these best constants. And now omega could be anything. Could be disconnected, next, no problem. Okay, now the problem makes sense. Okay, any questions?
So in the Heisenberg group, what is the geodesic hull of a ball?
It's between the ball and twice the ball.
Okay.
Something in the middle. It depends, of course. I don't have a better description than that. I can tell you at the end of the talk some interesting questions about this. If you remind me, I'll tell you. Okay.
Okay.
But besides this type of sandwich, I don't have much to say.
Okay.
Okay. And now. And please tell me just to skip this part if you like. I mean, I'd be happy because you all know this much better than me. I want to just say some few words about sub-Riemannian manifolds, what they are. I'm sure you all know. So again, I wasn't planning to assume anything, but of course in this seminar, so feel free to tell me to just skip ahead. But I will proceed, and if you want, you can interrupt. So I should say just one slide at least. What is a sub-Riemannian manifold? So so we start with a nice smooth connected differentiable n-dimensional manifold, and the idea is like in many physical systems, you're not allowed to move in any direction on the tangent bundle and the tangent space. There's a distinguished set of directions called the distribution in which you're allowed to move. So formally, this is a submundle of the tangent bundle. The distribution is denoted by D, and we can always assume that it is spanned by, let's say, M, even globally defined vector fields, x1 through xm. And the dimension of this distribution is called the rank. And the interesting situation is when the rank is strictly smaller than n, then you get a strictly sub-Riemannian manifold. And in all of our examples, the rank is going to be constant, okay? So then you define an inner product, just as you do in the Riemannian manifold, but you define it only on the distribution. And finally, of course, a condition which will always be enforced for us is Hermander's bracket generating condition. This is the assumption that the iterated Lie brackets of all of these vector fields already generate the entire tangent space. This is, of course, very important because this makes the distribution what is called completely non-integrable, right? So you're able, there are no integrable submanifolds. You're able to reach from any point to any other point within a finite amount of time. So as I already said, is that okay? I mean, I'm going fast, but I'm assuming everybody knows what I'm talking about. Is that okay?
Yes, go ahead.
Yeah. So you're only allowed to move on horizontal curves, right? So what is a horizontal curve? It's a map from the interval 0, 1, and by the way, all of our geodesics curves are always going to be parameterized on the interval 0, 1. So it's a map, let's say absolutely continuous map from the interval 0, 1 to the manifold, so that the derivative always lies inside the distribution. And then once you have a horizontal curve, you can just calculate its length, just as you do in the Riemannian setting by this this expression, which does not depend on the parameterization. And now this gives rise to the so-called Carnot-Theodori sub-Riemannian metric. So the distance between 2 points x and y is given by the infimum over all lengths of horizontal paths which connect x and y. Okay, so as we said, by Hermander's condition, this thing is always going to be finite. This is the Chow-Rashevsky theorem. But if in addition, as a metric space, this space is complete, then we know that this infimum is always going to be attained. And a horizontal curve on which this infimum is attained is called a distance minimizing geodesic. I'll just say geodesic, okay? So these are geodesics in our sub-Riemannian manifolds. And finally, one last thing I'm going to need, but I'm not going to define it because you know the definition much better than me. We're going to say that our sub-Riemannian structure is called ideal if, as a metric space, it is both complete, it is complete, and there are no abnormal, non-trivial geodesics. So what is that? Again, I'm not defining. This has to do with the regularity of the endpoint map. To be honest, I've never really understood the definition. Maybe at the end of the discussion, you will give me some intuition. But let me just kind of reassure you that essentially almost all of our examples are always going to be ideal. And furthermore, being ideal is a generic property. Okay, so I think if the distribution is of rank at least 3, then in an appropriate genericity sense, this is a generic assumption. So we don't have to worry about that. Okay. The next slide, which again, you all know, of course, I'll just have to quickly describe the most basic sub-Riemannian manifold. This is the Dieth Heisenberg group HD. So what is this? First of all, it's ideal. Let's get this out of the way. No problem with idealness. This is a Carnot group. So this means a Lie group, which is simply connected, which is nilpotent and connected. And in this case, and this Lie group has a certain stratification of its Lie algebra. And in this case, it just has 2 strata. It's a step 2 Carnot group. In fact, it's even corank 1. So I'll explain. First of all, what are the elements of this group? So as a real vector space, this is 2D plus 1 dimensional, but it's convenient to think about this as a d-dimensional complex vector, z1 through zd, and an additional vertical direction, which is just real valued. Okay, and the group action is just the usual additive group structure on the first d complex numbers, and the entire action happens, the whole interesting thing happens on the last vertical coordinate, so there's some twist going on here. So this is a Lie group. It has an invariant Haar measure, which is a bi-invariant Haar measure, in fact, which is very easy to check. That is just the usual Lebesgue measure in 2D plus 1 space, real space. And what is the distribution here? So as I said, the rank, so the topological dimension of this space is 2D plus 1, but the rank is 2D. So the corank is 1. What are the 2D generators of our distribution? Of course, we would like to have some compatibility with the group structure. So you want to choose generators which are invariant under the group action. So what we do is very simple. At the origin of the group, we just choose these horizontal, the first 2D, you think of these this D complex numbers as 2D real directions, and we choose the 2D generators to be partial xk and partial yk. And then this is at the origin, and then we move these generators via the group action. And if you make the calculation, you will see that you get these guys, which are now xk and yk. So we have 2D of those, and they generate the distribution. And so this means that at the origin, the only illegal direction to move in is the vertical direction in this last coordinate. And as I said, it's corank 1, so it must be step 2. So as soon as you take the Lie bracket of x and y, you immediately see that you will get exactly the vertical direction. And that's it. You already generate the entire tangent space. So this is a step 2 group. The best thing I have to say in this slide is this. It's not even mine. It's this beautiful graphic, which is courtesy of Nate Eldridge. So this is the unit, let's say unit geodesic ball in H1. So H1 is a 3-dimensional manifold, which there's a natural parameterization, which we can identify this in exponential coordinates with R3. And then this is its unit ball. And if you know a bit more, so you see it's kind of an apple shape. So this kind of, if you know a bit more, it confirms what Monty Rickley showed, that the geodesic balls are not geodesically convex, right? It's kind of a strange shape. And another nice thing that you see here is this blue line over here. This is a geodesic in our sub-Riemannian metric, which connects the origin with the North Pole. And of course, it's illegal to move right in the vertical direction. So what the geodesic does is it swivels around, because by swiveling around, because the Lie bracket of x and y is exactly the vertical direction, you are able to make a vertical movement at the end. Okay, so basically, these guys, the Heisenberg groups, are kind of the sub-Riemannian analog of flat Euclidean space. But of course, they're different, right? So the topological dimension is 2D plus 1, but the Hausdorff dimension of these guys is 2D plus 2, because the Hausdorff dimension of the vertical axis is not 1, but rather 2, because you need to work twice as hard to move in the vertical direction. Okay, so this is kind of what I had to say about Heisenberg group. Any questions? Probably the only question you have is, why did I spend time on this? Because you all know it. Okay, so finally, I think I can at least state our main result for this talk, which is as follows. So assume that you have any subset omega of the D Heisenberg group of diameter at most D, then we have the following inequalities which hold on any set omega, again, having diameter upper bounded by D. Poincarè inequality, LP Poincarè, and log-Sobolev with explicit constants. Okay, and notice that up to this factor of 1/4, the constants here are exactly what we had for Rn, or more generally for a Riemannian manifold with non-negative Ritchie curvature, right? So this pi squared over d squared is exactly the Li-Yau estimate, the sharp Li-Yau estimate. This constant over d squared is this folklore result about log-Sobolev. And this constant over here, I didn't say this before, but this is exactly the best, the sharp constant for the LP Poincaré constant on a manifold with non-negative Ritchie curvature, okay? So up to this factor of 1/4, it's exactly as in the Riemannian setting. Okay. Now I should mention that, of course, inequalities of this form have been known in the sub-Riemannian setting, going back at least to the work of, let's say, David Jerison. He has a very well-known paper, something like Poincaré inequality for vector fields satisfying Hermander's condition. So this is very well known, and of course, since that work, there have been numerous works extending, and proving these types of inequalities in the sub-Riemannian setting. But the point is that if you look at the literature, these constants are typically non-explicit, and moreover, they implicitly depend on the dimension of the manifold you're working on. For instance, via the doubling constant. Okay, so they're usually non-explicit depending on dimension. So to the best of my knowledge, this is the first dimension independent results on the Heisenberg group. You see nothing here depends on D. Okay, the same result holds for all HDs. And also it's nice to get kind of explicit constants, because again, I am not essentially not familiar with explicit constants in this business. Okay, so that's our main result. Now you may ask me, well, is this really particular to the Heisenberg group? And the answer is no. Actually, the exact same results hold for arbitrary Carnot groups of corank 1. They don't have to be ideal. So they hold for various generalizations of Heisenberg groups. So this is one type of generalization. Another type is if we work on an ideal, now it must be ideal, sub-Riemannian manifold. So here are a bunch of other examples which generalize the Heisenberg group, but then you may have to replace the quarter that appears here with some other constants. So for instance, for ideal generalized H-type groups of corank K, so the Heisenberg group had corank 1, but if the corank is K now, then you would get 1/4 to the power of K. On the Grushin plane, which is kind of a two-dimensional quotient of H1, you would get 1/8. On various Sasakian and 3 Sasakian manifolds with certain, you see the asterisk here means I'm hiding some condition about non-negative curvature, or sorry, a lower bound on these on some curvatures here, which I don't state. It would be 1/4 and 1/64. So in fact, there are a bunch of examples. If you look at my paper, there are a few other examples that you can find there. And in fact, I'm sure that the result somehow it was written 2 years ago, and I haven't been really following up. I'm pretty sure now that there are additional spaces for which the result will apply. But we will see what I mean by this when we talk about the proof. This is another kind of vague statement. In fact, the result applies on an arbitrary ideal Carnot group, but then it's not exactly explicit. You have to replace the 1/4 by something like 1/2 to the power of capital N minus little n, where capital N is some finite number, but it does have a meaning. But of course, at the moment, I cannot tell you what the meaning is, but you will see from the proof this expression and how it appears. Okay. So these are our main results. Any questions?
No.
Perhaps
yes.
not a question, a small comment. In what concerns ideal, you are right that generic sub-Riemannian manifold for distribution of rank greater or equal 3 is ideal, but if you stay with Carnot groups, that is not, unfortunately, not true. Moreover, if corank is, if you take Carnot group where corank is big enough, corank approximately dimension of manifold, subient manifold is something like a cube of rank, that it is never ideal. So sometimes it makes sense to study also this case. But this is a property of great corank, actually.
I see. Okay, thank you. Yeah.
Okay.
Also, are these constants sharp or
no? I mean, there's no reason to believe they're sharp. In fact, even from the proof, you'll see some room for improvement. But an interesting question, and again, I'd be happy if you asked me, but at the end, so what is, how non-sharp are they? What's an upper bound on the best constants here, right? I give a lower bound, right? What's an upper bound? That's an interesting question, and it has to do with what Luca asked me before. So, but maybe I can speak about this at the end, but I don't claim sharpness.
Thank you.
I have a question. One can obtain the sub-Riemannian Heisenberg group as a limit of Riemannian structures on the Heisenberg group, like just shrinking the typical vector more and more. Can one obtain this uniform estimate for all those Riemannian?
Exactly. No. So not
because for the Poincare inequality has been done.
I think so. I think the answer is yes, because maybe I will comment on it later, but I think that the answer is yes, because you have an MCP, a uniform MCP with the same parameter for all the family.
Well, okay, right. So there's no CD. So the point is that in your approximation procedure, the lower bound on the Ricci curvature will go to -infinity. So if you just use like the traditional approach of some CD approach, this will not work. If you use MCP, which is also, of course, what I'm going to use in the proof. So maybe we can, I'm happy to discuss if you can do the limit via the Riemannian guy, but let's maybe do this at the end, okay? I will try to remember. Okay, so let me try to tell you a bit about the proof, right? So I think maybe the proof is actually more interesting than the statement. So the proof will go through the theory of optimal transport. So let me kind of give you a crash introduction to this. So again, we're working on a metric measure space, complete separable, and we introduce the L2 Wasserstein distance, W2, between two probability measures, mu0 and mu1 on our space. So this P2 notation means that we're assuming that they have finite second moments. So what does the W2, the two Wasserstein distance between these two guys? What you do is you look at all possible couplings. Okay, so a coupling pi is just a probability measure defined on the product space, so that its first marginal is mu0 and its second marginal is mu1. And you try to minimize the, in this L2 sense, the total work you have to do to transport the first measure mu0 to the second measure mu1. Okay, and this is in the L2 sense, so this is why it's called W2. So it's not hard to show that this is actually a metric. And moreover, this W2 metric weakly metrizes this space of probability measures, P2. And in fact, if the original space is complete and separable, this gives us a complete and separable metric space structure. Okay, so that's very nice. What is even nicer is that if the original metric space is a geodesic space, meaning that the distance between any 2 points is realized by a distance minimizing curve of minimal length, then the same also applies to this Wasserstein space. It also is a geodesic space. And that's great. This means that the geodesics on this Wasserstein space are given by a family of probability measures, mu sub t, indexed by the time by t, and I'll call t the time parameter. Okay, so basically, if you've seen, the internet, you have two faces, and you see a very nice kind of morphing of one face to the other. Typically, what people do is indeed they use optimal transport to do this morphing, and by varying the parameter t, you kind of change the interpolation between the starting measure mu0 and the end measure mu1. Now, just a matter of convenience, this is something which I prefer a kind of an equivalent language, which is more convenient for me. Instead of thinking about the Wasserstein geodesic, which is kind of a family of probability measures indexed by the interval 0, 1, it's more convenient to lift this entire family to what is called an optimal dynamical plan. This is a single probability measure nu, but it lives on the larger space, the space of geodesics on X. Okay, so you can always lift this family of probability measures living indexed by the interval 0, 1 to a single probability measure living on the space of geodesics, which are, as I said, parameterized on the interval 0, 1, so that this lifting has the property that if you push forward nu by the evaluation map E sub t, so the evaluation map just takes a geodesic gamma and it gives back its value, its location at time t, then you get back your original family mu sub t. Okay, so the ET is basically going down from the space of geodesics to X at time t. Okay, so you can always go back and forth, and I prefer working with one probability measure upstairs. Okay, and we'll denote by opt geo mu0 mu1 all such optimal dynamical plans having the corresponding correct values at time t equals 0 and at time t equal 1. Okay, so this is just a convenient notation. Okay. Another little definition that we're going to need, it's not going to be too important, but I'll say that our metric measure space is a Monge space if for any two probability measures, mu0, mu1, we're going to assume that the first one is absolutely continuous with respect to the ambient measure m, but we make no assumptions on the target one, on mu1. could be discrete. Well, the only thing, let's assume that its support lies inside the support of the ambient measure, okay? But under these conditions, now we would like to require that three things hold. First of all is the requirement that there is a unique optimal dynamical plan, okay? So there's only one recipe to interpolate between mu naught and mu one, okay? There's only one way to do this. That's a very natural requirement. A second requirement is a strengthening of the first. Actually, we're going to require that nu is induced by a map. In other words, given a point x, there's a recipe, there's a map that tells x where it has to go, and then it goes along the geodesic to the target point y. Okay, so this, of course, it's classical and easy to show that this yields uniqueness of the optimal map, but it's stronger. It really means that you're not splitting atoms. So if you have a point x, you don't want to split its mass, one half go here and one half go here. No, there is a recipe and you follow the recipe and then you move along the geodesic. So this is the second property. And the last property is about preservation of regularity. So basically, if we denote by mu t the corresponding Wasserstein geodesic, remember we are assuming that the source measure mu naught is absolutely continuous, and then this is the requirement that absolute continuity is going to be preserved along the whole Wasserstein geodesic. So for all time t between 0 and 1, of course not including 1, because at time 1 we make no assumption. The target measure could be discrete. But as soon as one of the endpoints is absolutely continuous with respect to m, then the entire Wasserstein geodesic is also absolutely continuous. Okay, so this is kind of a regularity assumption. So, you don't really have to remember all of this. Do we know any Mon spaces? Yes, of course. So any complete Riemannian manifold, in fact, you can use not just the Riemannian volume measure here, you can use any strictly positive, smooth density psi. This is going to be a Monge space. This is due to already 20 years ago by Cordero, Roscan, Makan, Schmuckenschlager. And finally, in the sub-Riemannian setting, but now you have to assume something. For example, ideal certainly works. Any ideal sub-Riemannian manifold is also a Monge space. This is due to Figali and Reform. Okay. Okay, and now we finally come to kind of a main ingredient that we're going to use, which was actually our inspiration for this work. So in the Riemannian setting, this is completely classical, going back to the work of Cordero, Makan, Schmuckenschlager. But in the sub-Riemannian setting, this is very recent. There are two instances of this theorem. The first is due to Barilari and Rizzi. If we have any but ideal sub-Riemannian manifold, this theorem applies. And there's another instance, which is due to Balogh-Kristàly-Sipos. They don't need to assume ideal, but they work with co-rank 1 Carnot groups. Okay, so the theorem states as follows: assuming we have a sub-Riemannian structure, one of these guys, okay, marked above. In particular, we know that they're Monge. So these are Monge spaces. And if you take two measures, source and target measures, let's say compactly supported, which are both absolutely continuous, then we know by the Monge property that there's a unique optimal dynamical plan which interpolates between them. And we know that if you look at mu t as the associated Wasserstein geodesic, we know that it's going to be absolutely continuous for any time t. So let's denote by rho sub t the density of at time t. Then the requirement is, or not the requirement, sorry, the theorem states that you have this type of interpolation inequality. So if you look at the density at time t, evaluated at almost any geodesic at time t, and you raise this to this negative power of 1 over n is the dimension, the topological dimension, then this can be lower bounded by interpolating whatever happens at time 0 and whatever happens at time 1. But you do this using these kind of exotic interpolation coefficients. Usually when you're talking about concavity, you have 1 minus t and t, but here no. You use these measured distortion coefficients, beta t. Okay, what are beta t? Let me give you the definition. It's rather simple. So you take beta t between the point x and the point y. So take a point x, take another point y, and draw a ball, geodesic ball of radius r around y. Look at all geodesics connecting x and any other point inside the ball. and consider ZT. What is ZT? These are just the T midpoints of all of these geodesics. Okay, the T midpoints. Take the measure of ZT, this purple guy, divide by the measure of the ball, marked in blue, and take the limb sup as the radius of the ball goes to 0. Okay, that's the definition of these measured distortion coefficients. And indeed, these coefficients somehow capture the curvature of the space. Not just the space, also of the measure, because you're using the measure m here in the numerator and denominator. So for instance, if you're on on a space with positive curvature, then geodesics, they become kind of fat, right? So geodesics are fat on a sphere. So maybe this guy will have large volume. On the other hand, if you're in hyperbolic space, then geodesics tend to kind of be very, very narrow, right? So maybe they just pass through this guy, very narrow guy on their way. So this will be small. So certainly this tells you information about curvature. Okay. So that's the theorem. Now, of course, on
Emanuel, there is a question by Zoltan.
Okay.
Hi, Emanuel.
Hi, Zoltan. How are you?
Hi. Good. Thank you. Very nice talk. I think there is a small typo with the beta t. You need to divide by m of b r times dy, right? So you need to make the Bosma.
No. So I think you're using a normalization which was also used by Cordero-Makan-Schmuckenschlager. I'm using the normalization from the Barilari-Rizzi paper. It's just a matter of normalization.
Oh, okay.
Don't worry about
it. In that case,
yeah. Okay. I think I'm correct, right, Luca?
Yes. Otherwise, if you define them in the other way, then you have an extra t appearing in front of the beta.
Yeah.
There are different conventions.
Yeah, just the American convention. Okay, so of course, on an n-dimensional Riemannian model space with Ritchie curvature equals to k. So k positive, this is a sphere. K negative, this is hyperbolic space. K zero, this is just a flat Euclidean space. Of course, one can make the computation of what these beta coefficients are. The usual expressions involving sines and hyperbolic sines and so on. I can write them out, but there's no point. I thought I'd spare you. Let me just call these guys the model Riemannian coefficients by tau. I'll call this. I think this coincides with the traditional notation from optimal transport theory. Tau, of course, they depend on k, the Ritchie curvature, on capital N, the dimension, on t, which is the interpolation parameter. And when k is not equal to 0, it's also going to depend on the distance between the points x and y, on theta. Okay, but this is the only thing it depends on. So we can write an explicit expression. Let's just give this a name, tau. And of course, by classical comparison theorems from Riemannian geometry, you can immediately show that if the dimension of your manifold is at most capital N and the Ritchie curvature is at least capital K, then these distortion coefficients are going to be at least the model ones. Okay, again, classical Riemannian comparison theorems. And I believe that this kind of observation, after seeing the paper about Cordero-Makan-Schmuckenschlager, this was the kind of inspiration by the for the celebrated works by Sturm and independently Lott-Villani, already more than 15 years ago. It turns out that this kind of interpolation condition, curvature, actually is a characterization of having a non-negative, on having a lower bound on the Ritchie curvature and upper bound on the dimension. So their idea of Sturm-Lott-Villani was to actually use this as a definition of what it means for a general metric measure space to satisfy the curvature dimension CDKN condition. You see, because usually when you talk about curvature, you need to take two derivatives, but for that you need a differential structure. To talk about this, you don't need anything. You need a Wasserstein space, and that's it. There's no differentiable structure assumed. And indeed, since their condition has been introduced, it's become very, very successful. Nowadays, you can take your favorite theorem in the Riemannian setting, and nowadays you probably know how to prove it in this very general abstract metric measure space setting satisfying CDKN. Okay, so this theory is very successful and powerful. Let me just give you their definition We don't need their most general definition. In fact, the definition of Sturm-Villani is a bit different in general, but on Monge spaces, no problem. Everything simplifies, their definitions coincide. So I'm just repeating what I basically just said, that their definition of CDKN on a Monge space is this interpolation a requirement on Wasserstein on W2 geodesics with the Riemannian coefficients here, with the model Riemannian coefficients tau Kn. Okay, so that's the definition of CDKN. I'm going to need also the definition of MCP, which is was introduced by Sturman in the Bentley Otta a few years later. This is basically stands for measure contraction property. What is this? This is a relaxation of the CDKN condition. Look at this expression on the right-hand side. You know, it's kind of complicated. It's annoying. You know what? Let's just remove the second term here. Why not? This I cannot mark it. Just this guy. Just the second term here. Remove it. So of course we made the inequality weaker, right? So it's certainly weaker. But you know, if we remove it, then we don't need to talk about the density at time one. So why don't we don't need to assume that the target measure mu1 is absolutely continuous. Let's just assume that it could be anything, even discrete. And in fact, if we're assuming that it's discrete, we might as well assume that it's just the delta measure at a point. It's equivalent. So this is why it's called measure contraction property. We're basically contracting, we're all optimally transporting to a single point. Okay, and it's certainly weaker condition. Okay. So finally, I can explain to you why is the sub-Riemannian setting so challenging. And in fact, I'm running very late due to my own fault and also the internet's fault. So Luca, please tell me how much time should I go on for more?
Well, I think we started a little bit later than you disconnected. I think you have 15 minutes, 10 minutes, 15 minutes.
Okay, I will
maybe
try.
even more, a little bit more if you want. It depends on what you want to say.
Good answer. Good. I promise to just say things that I will hope will be interesting to you, but you know, I cannot. I'll do my best. Okay, so let me explain why now I can finally explain why the sub-Riemannian setting is so challenging. The reason is this starts with the work of Julien in his PhD thesis in 2009, but he did this first for the Heisenberg group, but then recently he extended his observation to an arbitrary sub-Riemannian manifold. It turns out that any strictly sub-Riemannian manifold can never satisfy any CDKN condition for any value of K and for any value of capital N. Okay, so this means that this very successful theory of CDKN can never help us here, at least not directly, cannot be applied here. However, so that's the bad news. The good news is that Julien showed that the Heisenberg group satisfies the weaker MCP-KN condition. With which parameters? Well, the curvature parameter is 0. That makes sense because, as we said, Heisenberg is kind of the analog of flat Euclidean space, and moreover, it has a dilation operation. So if it holds for some value of K, it's going to hold with 0. So the curvature is expected at 0, but what is the dimension? He actually identified the sharp exponent for the MCP condition. Remember that the topological dimension of HD is 2D plus 1. The Hausdorff dimension is 2D plus 2, but the sharp exponent for MCP condition is 2D plus 3. Okay, so this was the first time I think that this very interesting number appeared, I think. And if you denote this by capital N and the topological dimension by little n, notice that 2 to the power of capital N minus little n is, of course, 4. And foreshadowing what's about to come, this 4 exactly explains why we get 1/4 in our results. Okay, it's exactly from this formula. Okay. So of course, since Julien's work, the MCP-KN condition has been established on a variety of sub-Riemannian manifolds. I'm sure this is not a complete list. I apologize to anyone who may have left, but it's really every few months there's a new result. So MCP-KN information certainly was known before our work in the sub-Riemannian setting. Okay, so let's go back to the Barilari-Rizzi and Balogh-Kristàly-Sipos theorem and see what we can do. Okay, so now let's start working. So we know that MCP-Can condition, people have already established this on a variety of spaces, the spaces that I've showed you before, you know, Sasakian and generalized H-type groups and so on. So we have this information. Now, of course, the beta coefficients are also about contraction to a point. So it's really a one-line exercise to show that once you have MCP, then you also get control from below on these measured distortion coefficients by the model Riemannian ones. Okay, so this is what we know. And now if we plug this into this theorem, then we see a very nice self-improvement property. Okay, because we see that we can lower bound both of these terms. So the MCP original condition is without this term on the right-hand side. It's just this inequality over here, just this one. Okay, but now thanks to this theorem, we know that we actually get control from both sides. So that's nice, but it's not so good still, because you see the power here is kind of the wrong power. You see, you get the model Riemannian coefficient, tau kn, but it's raised to this power of capital N divided by little n, which in the strictly sub-Riemannian setting is always strictly larger than 1. So this is a power which is strictly larger than 1, which means that when you go to the endpoints, when you go to time t equals 0 and when you go to time t equals 1, in order to get this really explains why no CDKN condition can ever hold, because under CDKN, you want these coefficients asymptotically near 0 and 1 to behave linearly. But here you get a linear function raised to the power of something larger than 1. It's going to decay too fast. So this really explains why no CDKN condition could ever hold. So this is nice, but not enough. So what can we do? Well, our very naive idea is to say, well, there's a very simple way to fix those powers, to make them 1. Let's just apply Jensen's inequality. Okay? So we can fix the powers to be powers of 1, but the price that we're going to pay this extra constant over here. And this constant is exactly the constant that you've already seen, 2 to the power of capital N minus little n. And then if you apply Jensen's inequality, you get this statement. Now the powers are nice, the powers are 1, but you get this extra constant in front. So let's turn this into a definition, and we're going to call this the QCD condition with constant Q. Why QCD? Because this is a quasi-convex relaxation of the original CDKN condition. So when Q is equal to 1, the Q is the slack parameter. When Q is equal to 1, you get exactly the CDKN condition. Okay, but this QCD condition gives you a little bit of room. You get a nice little extra constant to fix your problems. Okay. So why do we like QCD? Because of the following one-dimensional reason. Okay, basically, if you have it's an exercise to show that if you have a one-dimensional density on the real line, well, let's say continuous on its support, but it's not important. And you know that this one-dimensional space, L1 is just Lebesgue measure. So if you know that this one-dimensional space satisfies QCD with parameter Q here, then this is exactly the same as the following statement. You can always modify your density H and turn it into another density F. And when I say modify, but by no more than a factor of Q. So F is sandwiched between H and QH. But now this modified density satisfies exactly the CDKN condition. Okay? So don't worry about it. I mean, I'm low on time. It's basically a lemma. It's an exercise. The problem is that it's really a one-dimensional property. This will never hold in
Hello,
Rn.
Megan. How are you today?
Hello?
Hello, I'm good, thank you. How are you?
Oh,
Fine, thank you. Would you like
So
to
I think he
share
didn't mute
the
himself.
tutorial problem today in the chat?
Wait a second.
I
Trying to
can-
mute him. Okay, he
Okay,
did
I-
mute himself.
I did mute him, yeah.
Okay, go ahead.
Okay. Anyway, so this is really a one-dimensional property. Okay, so this is not true in Rn. In Rn, you would not see Q. You would see Q and some function of the dimension. Okay, so this is really a one-dimensional property. So we really need a tool to reduce our question to dimension 1. Okay, and now comes probably the most interesting part of the talk. And of course, I don't have time, but I don't know. So do I have 8 minutes? I don't know. Do I have 8 minutes or something? Or tell.
What time is yeah, you have 5 minutes, okay?
Oh, okay. So basically, what we're going to use is localization. So very vaguely speaking, localization is a paradigm for reducing various geometric and analytic inequalities to dimension one while preserving curvature lower bounds. So what do I mean by this? Very roughly, again, I'm going to be vague. If you have some nice function which integrates to zero on your space, localization now in modern language is a disintegration of your original measure M into a family of simpler measures MQ, where MQ are satisfy three properties. First of all, they're one-dimensional. They're basically supported on distance minimizing geodesics. So this is a very nice simplification of the measure M. But so far, I didn't say much because, whenever you do Fubini theorem, you're basically doing disintegration into one-dimensional fibers. Whenever you're using polar coordinates, you're basically making a disintegration into one-dimensional rays with a density of, r to the n-1 dr. So we use explicit disintegrations all the time. But this disintegration is not explicit. It's adapted to the function f. So the second crucial property is that this disintegration keeps the balancing condition of the function f. So it's adapted to your function f. And finally, thirdly, these simpler one-dimensional measures MQ will all share the same interpolation lower bounds as your original measure M. Okay, so if the measure M has some type of curvature dimension type condition using interpolation, then all of these one-dimensional measures will also share exactly the same property. Okay, so this thing has a history. I don't have much time, but basically it starts with NRN in the work of Payne-Weinberger. It was rediscovered by Gromov and Vitaly Milman, and further developed by Kana Lovas-Shimonovich from kind of the computer science side. In the convexity community, which kind of in one of my several hats, I belong to this community as well. We've been using localization for many decades, and it's very successful. The problem is that this was really confined to Rn. And then there was a breakthrough work a few years ago by Boaz Klartag, where he managed to extend this paradigm to the smooth Riemannian setting using L1 optimal transport. Okay, so not L2, but L1. And then this was kind of adapted to the optimal transport community, and it was known by results by Bianchini and Cavaletti for MCP spaces, and by Cavaletti and Mondino, very influential work, on CDKN spaces. Our little contribution here is to note that actually this localization paradigm has nothing to do with these model Riemannian coefficients tau kn. It's completely general. So basically, whenever you have any interpolation coefficients, let's say continuous, there's some technical assumptions, but whenever you have tau naught for this coefficient and tau 1 for this coefficient, then if the big measure M satisfies this type of curvature condition, this type of interpolation condition, then what you can always apply localization, and this condition will also be satisfied by the one-dimensional measures. Okay, so for instance, of course, this recovers the previous results. You can get MCPKN if you use this, just make this zero, just forget about this coefficient, you get the localization result for MCP. You can recover the localization result for CDKN if you use tau naught and tau 1 to be the model Riemannian coefficients. And in our case, for QCD, which is what we need, you just use the coefficients, the Riemannian coefficients divided by our slack parameter Q. Okay, and this is what we need. So let me not say much more about that. And this will be my last slide now. Now I can kind of give you an outline of how our proof goes of our results. Okay, and I will finish. So you start with a good, nice sub-Riemannian manifold. Many smart people have already made the calculation and verified that they satisfy the MCPKN condition. And now if we plug this into the Barilari-Rizzi Balogh-Kristàly-Sipos theorems and apply our Jensen inequality, we will see that these spaces satisfy the QCD condition. Now, in all of our functional inequalities, remember that we have some test function which integrates to zero. This is our balancing condition. So given the test function, we use this to apply our localization result and reduce the problem to dimension 1. So basically now our problem is to find the best constants in a one-dimensional inequality in our Poincarè, log-Sobolev inequalities, but for one-dimensional spaces which satisfy the QCD condition. And the nice thing is, because our measures are supported on distance minimizing geodesics, then if the original problem had support bounded, if the set omega had diameter upper bounded by capital D, then all of our one-dimensional measures will also have diameter upper bounded by capital D. Okay, so it's exactly the same problem now. Now that we're in dimension 1, we can use our little one-dimensional proposition and modify our QCD density to another density F, where now F satisfies exactly the CDKM condition. And the only thing we do is pay a factor of Q. We make this modification. And now we just need to know the classical fact that if you have for many functional inequalities, if you know that the inequality is satisfied for a certain measure and you perturb the measure by a little bit, then still the inequality will be satisfied, maybe with a worse constant. This is usually called the Hawley-Strook type argument. For instance, for the Poincarè inequality, this is basically a triviality, but for the log-Sobolev inequality, this was done by Hawley and Strook. Okay, so basically, this just means that if you modify if you're interested in the density H, you want to know what's the best constant you can do there, it's enough to establish it for the density F and then pay the price of Q in your constant. And basically that's it. So this means, look at this line, this means that if you want to know what's the best constant for QCD densities, then we just pay a price of 1 over Q, and it's enough to know what's the best constant in the classical for CDKN densities. And that's it. That's just class. I don't even have to work for that, because for one-dimensional CDKN densities supported on an interval having diameter at most D, I just have to look at the literature. This is well understood. This explains why we get exactly the same results as in the CD setting, but we just pay a factor of 1 over Q. So for the Heisenberg group, Q is 4. For your other spaces, you can look at the literature and figure out what Q is. Okay. And basically, that is all I wanted to say. Sorry for going over time. I don't know what happened. Thank you very much.
Okay, thank you, Emanuel, for your talk.